between information theory and differential geometry, properly speaking. So she's thinking about information from a geometric perspective, which I find very interesting. And so thank you, Sueli, for sharing some of your insights with us today. Let's do 50 minutes and then a couple more minutes discussion, if that's okay.
Okay.
Please go ahead.
Okay. First of all, thank you very much for the invitation. It's a nice opportunity of interaction with the group. And so be welcome to this topic. As written before, the idea is to present the work we have been done in our research group here at Unicamp. And which relates some different topics of geometry to information area, I mean, communications and so. Okay, so as written at the summary before, this talk will be presented in two different topics. One is discrete geometry, and the second one is more differential geometry, both related to the communication area, right? So we'll start talking about some discrete geometry and applications to communications, different applications to communications. And then the second topic will be information geometry, which is essentially the geometry of statistical manifolds and applications, right? So let's start with lattices. So lattices are a discrete set of points in the n-dimensional Euclidean space given by integer linear combinations of a set of independent vectors, right? Problems related to lattices intrigued very important mathematicians like Kepler, Newton, Gauss, Lagrange, Minkowski, at least since the 17th century till today. A classical problem related to lattice is the problem of a sphere packing, which has application in many areas, right? In dimension 2, 3, 8, and 24, it's proved that the density semi-radius sphere packing in the space can be realized by lattices. The conjecture is that it is the same for all dimensions. The first proof for n equal to 3, right, which is the Kepler conjecture from 17th century, 1614, came the full proof in 2005. For n equal to 8 and n equal to 24, it came in 2007, that probably you have heard. Proved respected by Marina Vyacheslavica and Kohn, right? So, there are several lattice application communications since the 70s, at least. And these applications are related to both the reliability of transmission and for the security of transmission, right? For different kind of channels. So, one topic which is quite recent is this so-called lattice-based cryptography, which is currently a very important subarea of I will talk about this a little bit later. But one thing that is important to stress here is that an important international competition, which is proposed by the organism from the United States, which is responsible for regulating patterns, right? from it was in this competition, in the third round of this competition, right? From the 7 selected projects, 5 are Lattice-based, right? So this is a real, show the real actuality of this topic, right? So, okay. So starting with some Lattice preliminaries. Here we present the standard lattice in R2 to get some picture, right? So the lattice z to the square, the hexagonal lattice, which is generated by 2 vectors with 60 degrees, right here, and another lattice generated by 1, 2, and 0, 3. So a subset. So it's a lattice. Another characterization of lattice is any discrete. It must be a discrete additive subgroup of Rn. Right? A generated by base matrix of a lattice is a matrix which has as its columns the generator vectors, right? So this is an example of the so-called hexagonal lattice in 2 different bases, right? And here we also drawn some the paralleloptops relates to these different bases, right? In fact, two sets generate the same lattice if one differ from the other by an unimodular matrix, right? So we deal here with so-called full rank lattices, which means that the number of independent vectors is the same as the dimension of the space. In this case, the volume of the lattice is just the modulus of the determinant. And this volume does not depend on the particular basis of the lattices, since any base will have the same number for this determinant, the modulus of this determinant. Another concept which is important in application is the concept of fundamental region. A fundamental region is a region of Rn that tile the Rn by translations of the lattices. So, in the sense that if you translate this region by vectors of the lattice, we reproduce the Rn, and the intersection of those 2 different translations is they both intersect at most on their boundaries, what means the 0 measure, right, in the intersection. So 2 important fundamental regions are the fundamental paralleloptop, which we have shown, and the Voronoi region. The Voronoi region is the set for each point in the lattice, is the set of points which is at least as close to X to any other lattice point. That is this the definition. And here there are the Voronoi regions for the integer lattice, the hexagonal lattice, and the other lattice posed there. So, what are Voronoi constellations which are used in communications? We consider two nested lattices, one contained in the other. And of course, since this is a commutative group, we can consider the quotient, and this will be used in the coding process. And a Voronoi constellation will be when you have a pair, which one is the fine lattice and also the coarse lattice, is the sets of the fine lattice which are contained, the representative of this cosets which are contained inside a Voronoi region. This is their examples. So this is a way to select points of a lattice in order we can work for communications, right? Because we always deal with a finite number of points, right? And this way, we still have some algebraic structure. We can add points inside and so, and have some, this is the Voronoi region of the origin. And it's important to have some symmetry and equilibrium related to the origin in this kind of selection, right? Another other figure of merit, what we used to call Lattice, is the packing density, the covert thickness, and the minimum product distance. The minimal norm of a lattice corresponds to the minimal distance between any 2 points of the lattice, because since we can translate in the lattice, this is the same that the minimal distance from 1 point of the lattice to the origin, right? This is the distance, minimal distance in the lattice. A sphere packing of a lattice will be realized by this minimal distance divided by 2, right? So in this way, the balls in the lattice with this radius just intersect on the boundary, right? And the packing density of a lattice is the volume of this packing ball divided by the volume of the lattice, which is the same as the volume of the Voronoi region. Because of this, the characteristics of a lattice, the styling of the lattice, this is the same part of the Rn that will be covered by this ball, right? This number is the percentage of the Rn which is covered by those balls, right? The center density is another definition that does not use the volume of the unit or the ball of radius 1, but it's also this is done just to compare lattice in the same dimension. Here it's more intuitive. You deal with the first definition. Right? So here we have this. We exemplify with the same lattice we have presented before. The packing density for the Z2 lattice is a half. It is the packing radius is a half because this is 1, right? So the half, and the packing density is like 78%. The packing density of the hexagonal lattice is 90%, and the packing density of this lattice is 52%. Just to have an, and it can be proved that this is already proved 19th century, right? That this lattice has the best packing density between any packing balls in the plane, right? So going ahead, this is a cut from the so-called BCC lattice, which is the lattice which is formed by think about a cube. I put some point in the middle, and I set the balls here to think about the packing balls, right? In the corner and in the middle, right? If I spread this into R3, this is so-called the BCC lattice, and it has some bases like that, right? So this is the sides of a cube, and this is the center of the cube. And this is the FCC lattices. But here we are centering the faces of the cube. The center, the ball is centered the faces of the cube, the points in the lattice and the middle of the faces. We are going to see next that this is the best packing density. This is the best packing density realized in R3. That one I mentioned, that was conjectured by Kepler in 1612, and proved this century, right? This is exemplified by this ball packing. Another concept is the sphere covering of a lattice. This is here we take the shortest radius that translated by elements of the lattice, we can cover the Rn, right? And for the covering thickness is the volume of this ball divided by the volume of the lattice, which is the volume of the Voronoi region. Right? Again, the smallest is this number. This number is always bigger than 1, right? As the best is the lattice regarding this concept of covering, right? So here is the the covering of the Z2 lattice, the covering of the 8 hexagonal lattice, and the covering of the other lattice we set there. So we can see here that the hexagonal lattice again has best covering because the smallest number. This is the second, and the Z2 lattice in the third, right, for this example, just to have an idea. Then, so we say that two lattices are equivalent if one is obtained from the other from an orthogonal matrix and another constant. So one is a rotation scaled version of the other. Two equivalent less the same packing density and same covering thickness, right? Here, just a comparison. So we have the Voronoi region for the diagonal lattice, the packing radius, and the covering radius, right? Lattice quantizer is another concept which is used in communication, and it's defined like that. So, and it's related to the square distance, right? And the smallest this number, the better is the quantity. That's the idea. So this is the definition of quantization and some results on quantization. Again, the quantization is invariant, again, regarding scaling and rotation, right? And we go next, because there are many concepts. Here, we present what are the best proved and also the best known lattices in dimensions 1. So we just know what are the best lattices in dimension 1 to 8 and 16 and 24. I'm calling about packing in lattice, not general packing, right? So these are the lattices that are well known to be the best packing things. This is the kissing number, which is the number of points which are at minimal distance. This is the covering density, which are, so here in dimension 2, the A2 lattice, which is the version of the hexagonal lattice, has the best packing density, the best covering density, the biggest number of points, and the best quantization. So it's good for everything. When you go to dimension 3, this is not true, as I mentioned before. The best packing density is the A3 and D3 lattice, which is the FCC lattice. Instead, the covering density is by the BCC lattice, the body-centered lattice, right? And again, we have this, it's for kissing number, we have the same here, and the dual lattice correspond for quantization. Exceptional lattices, you can see here, this is not the same for which are good for everything. In dimension 8, almost good for everything. It's a very special property. And dimension 24, this is the Leech lattice, which is very special, right? Another topic I will just skip because we also use to deal with lattice with different measures. From now up to now, from what I talk until now, all the distance considered are the Euclidean distance, but we also use the LP distance on lattice, in particular the maximum distance and the taxi distance, or the lead distance, as we call in lattice, right? But I skip this, many topics. The product distance is not a distance, but it's a number which is important when you have a lattice for when you have lattices which are Rayleigh lattice, which has vanishing properties, right? When you have a communication through Rayleigh channels. So this is a number, so which is also used, which means that the product of all the coordinates of a lattice, and of course, if we have, since 0, 0, 0 is always a point of a lattice, right? Different coordinates to have a good diversity, and the product distance will be the minimum number of this product, right? I'll give an example, which is gets better. So this is the hexagonal lattice in the standard position, right? And it has diversity 1 because we have points with 0 in some coordinates here. And so the product distance here is 0. And here is the rotated version of the hexagonal lattice, which produces the maximum minimal product distance. So if you have some channel which is fading, as many channels in communications, like communication through cell phones are, this lattice, which is better than this lattice, the same packing density, the same covering rate, same covering density, but the product distance here is better than that one. So it depends on the kind of channel we consider, right? So here's some work we have been working. So I meant that some construction of lattice allow. This is a very number here. Usually, is very hard to calculate, right? This product distance, but for some construction of lattices, we can get this number from algebraic procedures, right? And here, usually we have some. The ZN lattice has better product distance than the best lattice in that dimension, right? This is the comparison here. Just to have an idea of that. So, regarding lattice coding for different channels, important parameters are, if you consider Gaussian channel, which means the noise is distributed to a Gaussian probability, right? So kind of a round distribution of noise. Important parameters here, packing density, Kiesling number, and shaping of a finite subset. What shaping here, this is the quantization of, if we consider a lattice, which points are chosen from a sublattice, and the Voronoi of the set must be good for quantization. So different properties from both lattices. One way we will ask from good packing density, and the other one we will ask for good quantization. Rayleigh fading channel. Here we have we require full diversity and big minimum product distance, since their probability is limited by a factor inversely proportional to this parameter, right? So, okay. Wiretap channels are kind of a channel that we intend both reliability from transmission from Alice to Bob, and of course security, regardless some intrude like Eve here. So we have to organize to get both. So, usually we have to use two different lattices in this kind of procedure, right? Usually we have two kinds, two ways of constructing lattices with more structure. And these two ways are, first, lattice construction from linear codes in ZKN, which are subgroups of ZKN, right? This Z modulus key, that's the notation, right? What includes the so-called construction A, B, C, C star. This can be used in many applications, right? And I'm not going to talk about this in this presentation. I just did focus on the second one. I have put some reference here for people that are interested in that. And I will focus on the second one, which are lattice rely on the structure of ring of integer of number field. This is to see that many topics of mathematics are included when you deal with this kind of, in mathematics of communication. So we have different sub-areas of mathematics that are applied, as we can see. Okay, so Last construction using algebraic number theory. I will go very fast also here. If you consider a number field of degree n and signature like that, and the ring of integers, right? We have this very well-known result. There is exactly n distinct k homomorphisms from K to C, and we can use this kind of homomorphism to construct lattices. We are going to use from K, from C to the N, right? Connecting all these homomorphisms. Usually we divide this in real monomorphism and complex homomorphism, and then each time we have a complex homomorphism, the conjugate is also part of this n distinct homomorphism, right? What results we have here? When you consider this embedded here, described like that, right? This is called the Minkowski embedding or canonical embedding. We also can consider some variation of this embedding, which is consider some totally positive element from K. And with this definition, that for totally positive, this alpha is positive for any of those homomorphisms. We can modify this in order to obtain another embedding. Both embedding can provide lattices, right? In this proposition, right? So if you have a kind of number field, some subset, which is a free modulus, so the image is a full rank lattice in Rn with basis such tal. The lattices are called algebraic lattices. So, and those lattices can be called if M is an ideal of the integer numbers of K, this can be considered ideal lattices.
Can I ask a question?
Sure.
Why are they called algebraic? Is it the case that these embeddings are polynomial?
No, they are called algebraic because they come from algebraic number theory. So just that.
Okay. So the embeddings, we don't know what they are sort of explicitly, or we just know they exist.
Yeah. I'm trying. This is very, as I told, I chose many topics to talk just to people have choice to look more. Depends on the background. Right? So that's the idea. So okay. I go very fast here and see. This is used in cryptography also. I mentioned this. Okay, let's see. Mm-hmm. Okay. So I will go very fast here, as I mentioned, because when a lattice is constructed like that, we can detect something which usually is very hard to set, which is the minimal distance of a lattice, and the product distance of a lattice. Right? If that's constructed, this is an algebraic lattice, we have this expression which comes from the construction and the field and so, right? That's the advantage of. This is a very small example. If you consider this the n-dimensional lattice, this is the definition of the Dn lattice, which is just defined by, here is wrong, this is Zn, are integer numbers, please, sorry for that. This is Zn, integer number, that the sum is even. This forms a lattice in Rn, and in R3, this corresponds, this is equivalent of the FCC, the density lattice in dimension 3. In fact, they provide the density lattice in dimension 3, 4, and 5, right? If you consider this extension of the rational numbers, this with this kind of, we have this alpha, for this alpha, and we can consider the embedding, we can construct the Dn lattice in a rotated version. And this rotated version will provide the best possible product distance, the greatest positive distance from that Dn lattice, right? The 3 lattice.
Just to be clear, is zeta 7 is the cyclotomic root?
What? Say it again.
What is zeta 7? Is it the cyclotomic root? What is zeta 7?
Yeah, exactly. Yeah,
it's the seventh cyclotomic root.
Yeah, exactly.
Cool. Okay.
Okay. So, in this paper, we have been working in, as I mentioned, this kind of topic, and we have constructed some rotated version of the DN lattice, right? This just to illustrate. So go ahead. Post-quantum cryptography, and this overview here, right? So the most commonly used cryptography protocols today are based either in elliptic curve or in the arithmetic number theory, the so-called RSA, right? The securities are guaranteed here because our current computers cannot solve the discrete logarithm problem and the integer factorization problem in a reasonable time, right? In 1997, Peter Shor has showed that this problem can be solved in quantum computers, right? So can be solved in quantum computers. Ever since, several researchers are trying to find secured post-quantum protocols for cryptography, which, independent of the advent of quantum computer, can be more efficient. So when we talk about post-quantum cryptography, we are not necessarily need to wait for quantum computer, but we can think about different cryptographic protocols that can be more efficient than the current protocols, right? So, and this, of course, is and of course, the possible advent of quantum computer is something that make people hurry up in this process, right? And currently, the most promising candidate system to post-quantum cryptography are based on error-correcting codes, multivariate polynomials, and lattices, right? As I mentioned before, from the 7 finalists in the third round, the base, 5 are lattice-based. So lattices are quite promising in this aspect, right? And what this has to be. So with less. 2 computational very hard problems for lattice in higher dimensions are the shortest vector problem and the closest vector problem. So, they have many variants and have used to cryptographic proposals since 1996. A very rough idea of this is that if you think about a private key, we can construct a lattice, like as mentioned, as an algebraic lattice or some lattice with special properties, and then I can decode properly. Let's say use the closed vector problems, and the public key just presents some bad basis that is very hard to decode. Right, that's the idea. Right. So one of these processes is called learn with errors. I will not enter in details here, and this is related to when we have this, we have some sample here and code. So and the security will be and this is the learn with error, which is precisely to use the lattice would come from algebraic number theory, right? So, and then it's related to the previous topic, right? So here I described very briefly this. Go ahead, how this is done. We have been working with this topic recently. What is interesting to mention that the 2 main authors of this paper here is one student from Ricardo Rabi, which is from the cryptography group in the the Institute of Computer, and a student of mine that has a lot of background in algebra, right? And what you propose in this paper is to extend, because the ring LWE is RLWE is based on the lattice constructed by the classical embedding, the Minkowski embedding. So we could show that we can use also the twist ring embedding, the one that uses that deformation there. And the security will be equivalent to the first one. And this allows more choices for lattices here, right? So another research in this, interesting in this aspect for people that are interested, some kind of, because this is very usual in cryptography to look for lattices that can have some problems in security, right? So other topic, right, which is also related to discrete geometry, right? The optimal spherical codes. So we have working this topic in three different aspects. Let's see. Some optimal spherical. What is optimal spherical code? Starting from the beginning. So if you think about, I want to set a point m points on a sphere in the n-dimensional space in order to have the maximum minimal possible distance. Of course, it's easy to infer application of this kind of problem, or which is the equivalent for given a distance d, if I needed to code in a certain separation to have the maximum possible number of points. So this is the problem to looking for optimal or good spherical codes. In dimension 2, this problem is easy, so they are just vertices of a regular polygon. But even dimension 3 is interesting that not always is intuitive, right? Of course, if you have just 3 points, the solution will be a triangle, a equilateral triangle in the equator of a sphere, right? If you have 4 points, again, it will be just a tetrahedron. Right? But you have 8 points. The best solution is not a cube, right? We can just load the distance between here, and so the solution will be the so-called antiprism, right? So just to have an idea, you know? And then, okay, what is known here? In n-dimensional, the simplex and the bi-orthogonal spherical codes are optimum. The simplex is equivalent to the tetrahedron in tree, right? And the bi-orthogonal code, spherical code, is also straight, so. But we also want usually some other properties when we think about communication, code in the code process, right? So more structure in the code. So we have been working with two different approaches to this topic: commutative group codes, which are associated to lattices, torus layer spherical codes in even dimension, right? They will be associated to lattice in each layer, because here we have a foliation of this, fibration of this, and spherical codes using Hoffer fibration, right? And some reference for that this is a paper which deal with this torus layer codes, which is the article, recent article, which is Henrique Miyamoto, Henrique Saep, myself, and there's a chapter in this small book we have, in chapter 5, that talk about this spherical codes, right? So it's kind of all this, right? So let's go ahead. Commutative groups are associated to lattice. How, right? If you think about this standard flat torus mapping here, right? So here we are going to, from one dimension to the double of the dimension this way. So this is the so-called flat torus map, right? And then what we do is that we can set some lattice here and some proper lattice here will provide some spherical code there, right? So that's the idea. Okay, so that's what I'm writing. The image inverse of this, by the torus map, it's a lattice. Right? If you have a commutative group code, it's a special structure of what you mean a group which is generated by matrix, right? The commutative and a commutative group, and free from reflection box. We have to exclude this. So in this case, the inverse mapping of a torus map is a lattice in the previous dimension. Okay, and then here there's some examples. We have 25 points in R4, right? And in these two examples, so the example in the right will be both have 25 points, right? And we have to choose the initial vector and some matrix, and the matrix will be defined by the division of the lattice provided here, right? So, okay. And this will be better than that one in terms of distance in R4. Because, and this is related to the density of the lattice here and the density of the lattice there, right? So just to have an idea. Okay, and then we can set for commutative group codes which have a hard algebraic structure, the number of points for a fixed D will be smaller than this number here, and this has to do with the packing density of the best packing density in the dimension L, right? Just to see how we can relate this. The torus-layer spherical codes is that because the density of a code which came from the flat torus map is not good, because we are in a manifold of dimension n containing the sphere in the double of dimension, right? So what we can improve this is to set some layers of tori, and then to set in each layer some code that come from lattice. We have to work with this, and that is the structure. We select some tori, so and construct this. We have to work with this kind of topic, collecting some code. They are not extremely dense, but have some nice structure. They are quite homogeneous in each layer, right? So here's some feature. I skip this. Spherical codes, finally, with this more recent construction we have done, which is a codes which is inspired by Hopf fibration. When we talk Hopf fibration is some kind of generalized of the Hopf foliation, which is just exists in few dimensions, right? And how this is done, the fact that I consider tori, but not flat tori, right? These tori are given by a sphere of radius of cosine of this angle and sine of this angle, right? And then we go to this from 0 to pi over 2, and then we can foliate the sphere in dimension 2n by this tori, and this allows some constructive spherical codes which we can go in dimension 2k, which were constructed step by step from the previous dimension. So we also propose a suboptimal decoding procedure, which does not require storing the code book and has some kind of complexity of this order, right? N log n, right? What is good for? Again, they are not dense, too much dense, but denser than, of course, commutative group codes. But they provide some, and they are really constructive and with good properties for encoding and decoding, right? So that's the idea. Okay, let's see. So spherical codes have been used in several applications, right? So like optical coding, and also some to improve the transmission over MIMO channel, multiple interns and multiples. Okay. Last topic, okay, which is, in fact, it's a long topic, okay. Now I'm going to talk about leaving discrete geometry and going to differential geometry now, okay. Okay, we are, although some topics of differential geometry already appear, like foliation and so, just now, right? So, okay. We are very much interested in this topic, which involves distance and dissimilarity measures in statistical manifolds of probability distributions, right? Applications, right? We are going to talk better this data analysis, image processing, radars, morphological classification. So here, these two references are general reference, and you can find many of these definitions and recent applications. So we have been working in particular with the so-called Fisher-Rao distance in normal probability distributions, some word missing here, including some application in data clustering for image processing. Right? I mentioned two of our papers here. I will detail next. Right? The importance here is more the reference in this paper that you can check many things there. This metric is defined from the Fisher matrix, which is related to relative entropy and used in application for learning. I mentioned more next, right? Example like natural gradients. So, a brief history for this area. Fisher matrix was introduced by Bernard Fisher in 1921. This is something like a father of modern statistics, right? Bernard Fisher, right? Connection between statistics and models and geometry are very old. I mean, so you have this, I'm quoting this Malanoves and Bhattacharya, and the most approach to the, what we call it today, information geometry, is the approach by Rao in 1945. And then we have some further developments. I just quote some here, right? And some important people to mention here, besides Rao, Amar, for instance, something, both are alive and working. This, it's impressive, really. Oh. Application problem, statistical inference. Application problem in statistical inference, Rao 1955. So we have this, the image diffusion, mathematical resonance image, morphology in image deformation, some applications that come along the years. I just set some focus on this, which I mentioned here. Modeling clustering experimental data in signal processing, data analysis, and learning processes. Those have been used for morphological classification, clustering financial return, and robustness in learning, so, and deep learning. So we are very much interested in this last application here. And we hope to have some presentation with more recent results. We are really put some focus on this topic now. I mentioned some previous work. So it's interesting. This work, for instance, is regarding classification of fishes in the Mediterranean, and it uses Fisher-Rao metric. I will mention next, right? Okay. So to start the motivation for this kind of distance. So suppose we consider here the probability distribution, normal univariate probability distributions. See, the parameter space of these distributions, this is the distribution, a normal distribution, a Gaussian distribution, is defined like that. So this is a function which has the integral on this, along all the line, the reals, is 1. Right? So this is a probability distribution, the usual probability distribution, normal distribution. And the parameter space is something which two-dimensional. So we have m, my for the media, and this for the covariation, right? So the distance between, so we need these two numbers to parameterize all these distributions. And when we look for the distributions, we can see that, this A, B are the parameter in the parameter space. And the associated distribution are this and this, right? C and D are in the parameter spaces. And this corresponds to this distribution, It's easy to see that those distributions are far apart than these distributions. The Euclidean distance here in the parameter space does not measure this. Yeah? So we are going to show that a proper measure here comes from the Fisher matrix, right? So, yeah. So for a statistical model of p-variable distribution described in a parameter space of any parameters, the Fisher matrix is defined like that. So this integral, this is the derivative of the log function, log composition of log function and the parameters. In the space of the univariate distribution described in the parameter space R2, as I mentioned before, the position of this line is wrong, but anyway, the Fisher matrix is this one, right? This one. If you calculate this, in that case, the Fisher matrix is this one. A closed form for the Fisher matrix, Fisher-Rao distance, can be obtained by association with the Poincaré metric in the half-plane, right? So it's easy to see that since we have this matrix here for the metric, the distance, the Fisher distance, will be square root of 2 of the distance of this term of here we are considering the Poincaré metric in the half plane, right? So if you use this relation, we can get a closed form for the distance. And for instance, in the half plane, when you consider the distance, the geodesic will be half lines and half ellipses. And this is the circle centered in this point. So the equidistant probability distribution associated to A, right? This is the circumference and the geodesic So to illustrate, right? So, of course, this is for univariate normal distributions, right? Multivariate normal distribution are defined the same way. This is the expression for a normal distribution in n variables, which is defined like that. Here we have the symmetric positive matrix, right? And here the distance between this vector. So this is the expression for the probability distribution, right? Of course, we can calculate, calculate the matrix for this distribution, but this is a manifold, just to remark first, this is a manifold of dimension n, which n the number of points of the mean, and plus this number, which the variation of this matrix here, right? Of the dimension of this manifold, right? No, this is an example of two normal distributions here in two variables, and here there's the level curves of this. So just to illustrate the normal distribution, and there's no closed form for the Fisher-Rho distance between two normal PDFs in this dimension n, right? So what you can do is that, just to illustrate and to set some bounds, is consider some special submanifolds, right? If you consider the manifolds, the submanifold, when the mean is constant, right? It's like in dimension 2, the vertical lines are geodesic, right? And the distance between two parameters, which describe the distance between the distributions, will be given by this expression here, right? This manifold is a totally geodesic submanifold, so we can set that even the big manifold, the distance will be the same, right? Another submanifold, we can calculate the probability, the distance, is when you consider diagonal, the matrix in the diagonal form, right? If you consider the matrix in the diagonal form, we can see that the Fisher information matrix will have this shape, and here we can set kind of product distance. The distance will be here, but the distance in the submanifold. And this two-n-dimensional manifold is not totally geodesic, but has a curvature this number. When we have the univariate normal distribution, as we have shown, it has this relation with the Poincare metric, and the curvature there will be minus a half. And this is the curvature for this submanifold. The big manifold has no constant curvature. Okay, we have considered the Fisher-Rho distance in this submanifold in the simplification for Gaussian mixture models using the hierarchical cluster algorithm. This is used for image segmentation. We also use the expression for all the submanifold from what we can get a closed form to derive upper bound for the distance in the general manifold of multivariate distributions, right? This is the results that can be found in this paper, right? Okay. I will comment some interesting fact that to stimulate people to look for some problems to solve in this area, that there are some specific journals to follow recent results in application of information geometry. One of those is Information Geometry, on the journal of Springer, which is called Information Geometry, and the other is Entropy, which is from the editor MDPE. Just to have some examples for you to have an idea of how much geometrical they are, right? One, the title of some 2021 edition, some self-similar solution of the Hessian flow, distribution of concentration convex of compact symmetric space, theorem for statistical manifold. Yeah, we have lots of things in geometry here, even with just perspective of applications, right? What is that? So, okay. Okay, in this presentation, it's a brief overview, really overview approach of discrete geometry and differential geometry themes related to information, with focus on topics we have been working in our research group. One thing important to stress is that for us has been very crucial the interaction with the research from different areas in order to get some problems that are really meaningful for application. So that even if we don't consider the application, the problems, the approach is useful. Right? Okay. And in this sense, what is interesting, even if you do something quite geometrical, so our paper, one of our papers of 2015, which is a geometric approach of just Fisher information network, right, has been quoted by many, more than 100 citations, because people that work in application are interested in understand better what is this Fisher metric is, and so that's it. Okay, I will close this and be open for questions. I return to the topics if people are interested on, right? So special thanks for the organizers for this opportunity of interaction, which is very valuable for us as a group, for my co-authors and my PhD students, for fruitful discussions and collaboration, even in the organization of this presentation, and of course to all attendants of this talk. Thank you.
All right, let's thank the speaker, please. Okay, we have, shall I take 5 minutes for questions and a little discussion? Do we have questions from the audience? Gustavo, go ahead.
Yes, my question is, at the end of the talk, you have talked about the statistical manifolds. Is there work which shows that we can exploit geometrical properties of these statistical manifolds in order to, for example, inference purposes, for instance, for developing estimators for random variables?
Could you say it again, please? What's the question?
Even the whole question.
Yes.
Is it known if there is a way to exploit geometrical properties of the statistical manifolds to tackle classical statistic problems, for instance, developing estimators?
Okay. We have some facts that are proved. Okay. For instance, that the Fisher-Rao method statistical, satisfies the condition of statistical sufficiency. I mean, this allows it to be applied in many statistical approaches, right? And also, of course, in the data analysis that have been done recently, as I mentioned. So, but one thing we are very much interested in, as I mentioned, we have interacted from people from electrical engineering, from computer science, but we have not till now interacted to many people from statistics. This is one goal, to understand better what are the connection between the statistical properties and the Fisher-Rao metric. We understand, we are looking to understand better this. So that's it.
I can give an example in which I'm looking at this theory for the purposes of supervised machine learning. This is something I haven't discussed with Sueli yet, but was inspired by her paper, so with one of her co-authors, Cristiano Torrezan. So if you consider the problem of two distributions which are sufficiently far away, but they're evolving sort of inertially, right? So they're evolving along geodesics on this hyperbolic manifold. Then you want to be able to estimate for how long you can allow the system to follow this dynamics before these distributions overlap too much, right? So essentially they would evolve along some geodesic cone, and so long as the cones are not intersecting, you don't need to supervise the your algorithm again. So this estimation of supervision time in supervised machine learning, there's a procedure that can be derived exactly from the stuff she just explained. So we're looking into that, and it's this is work in progress, so I have nothing to report. But the whole discussion has been inspired by this, right? So if you start sufficiently far, and you move, and these two distributions move inertially, then we can estimate minimum amount of time before they actually overlap too much, before they actually get too close, and that's in the Fisher-Rao metric. So there's a lot of applications one can derive from this way of thinking about distributions as lying on a manifold with a distinct hyperbolic metric. This is just one example of the things you can do.
Well, this is quite interesting. So are you using the Fisher-Rao metric?
We're literally reading your paper again and again. It's just, yeah, absolutely, yeah. It's the geodesics in the Fisher-Rao metric. They determine some cones, so you have some area that gives you a cone, and before these cones overlap too much, you don't have to supervise your algorithm again. So, but I don't have a theorem to report yet, but we're working on this topic, and it's directly inspired by what you wrote. It's we're just following your paper, using the stuff the closed formulas you computed there, and the negative sectional curvature and rest of it. Yeah.
Okay.
Totally.
Oh, this is very nice. We should talk on that. So very nice. So it's
yeah. Let me get the estimates right, and then we're doing some implementation. This is work in progress, but just give you one example of the kind of stuff we can do. Okay. Are there any more questions from the public? If not, then I would like to raise an issue benefiting from Marcos Alexandrino from USP, who's here. So this guy, for instance, is a specialist in Riemannian foliations, right? Has been thinking a lot about these Riemannian foliations. And I thought, so the problem of sphere packing, right? So distributing points, as many points as you can on large dimensional spheres, has been addressed by the speaker in terms of, and some collaborators, in terms of foliating spheres by tori. But that's just one way we can foliate spheres. I could imagine having more sophisticated foliations, especially in higher dimensions, and so that you can guarantee that if the leaves are sufficiently far apart, and if the typical leaf has some interesting structure, then you could maybe pack more points, or pack points in a systematic way, which is also a good thing in coding theory, right? But using more sophisticated, maybe singular foliations. So that's Marcus. Maybe you can bring some insight into this. Are there more creative ways to foliate spheres?
Right now, well, first of all, I would like to congratulate Professor Sueli. That was a very nice talk, a little far away from my knowledge, but we are here to learn. So thank you very much, Professor. And about your question, right now I have no clue. We have this class of Lusternik that is usually related to this topic. I was looking for some cross-reference between Lusternik categories, and while Sueli was giving her talk, but I didn't find a direct application in computer area. So packeting for us would be a little related with the Lusternik category. But about the foliation in sphere, what we are right now trying to find out maybe a little related with the quantum mechanics or quantum computations are these kind of generalizations of Hopf fibrations. So Hopf fibrations are seen as a pre-image of a polynomial that we can, for example, Hopf fibration goes from C2 to R3, and when you through a map that we construct using matrix Pauli. And this is in fact the average operator. You have three observers that you give through these three matrix, Pauli matrix. And we calculated the, how you say that, valor esperado, expected value.
Expected value, yeah.
Value. And this kind of thing can be generalized. What Leonardo is trying to find out right now is how to do that for something that is not just a half spin. This is the description of half spin, but we were interested to try to understand that for a more complex system. So right now, the kind of relations with possible applications that we are giving a look was in that directions, more in the directions of quantum computations. But we certainly can think a little about packing and how this applies to Lusternik category. And in particular, I'm quite interested to see this developing that you just talk right now. This may be the union of different areas. So your current work may be a kind of the first bridge between these two different areas. Probably I'm a very pure mathematician. Professor Sueli clearly has a very general culture, but it would help always to have someone in between. So we are very interested to see the development that you just cited. But right now, as I say, about packaging, I would try Lusternik category. Do you know this concept, isn't it? This you cover by small contractible subsets. And there are several applications using Lusternik category and bot functions. So you can use that for discrete bot functions. So the possible applications of Lusternik category in computation is normally related with the how you say that the people
sorry, so you foliate spheres by spheres.
Yes, by small disk. You need contractible subsets. Lusternik category is this number of smooth contractible subsets, the biggest that you can cover it. And the advantage of the Lusternik category is that it gives you lower bound estimatives for bot functions. And bot functions are used in computations, in graphical computations. I saw there was a nice guy in PUC-Rio, a French guy who's used this kind of things. But I'm not sure it has some applications for packaging right now. I saw something relating bot functions and then probably discrete bot functions with the Lusternik category. Yes, that was right now the present keywords that I would remind, but this concept that she just bring, I will need the time to think about.
Tell you what, if you can maybe later explain to me how this Lusternik category works. I mean, I don't know anything about coding theory, but I have spread some points over spheres in the recent past. So at least I know what these guys like. I don't understand the applications, but I know what
they are. How you
I know how to make Sueli relatively happy. So if you explain it to me, and then I can maybe bridge into a discussion with our students.
I can do that later.
Cool. Yes, let's do this later. Yeah. Nice.
But again, congratulations. That was a very interesting talk. Thank you. Thank you very much, Sally.
Yeah.
Okay. Thank you for this. Lusternik, I haven't heard of this. It's a different topic for me. So what should be some reference to look for?
I will just, I'll give a look and send you through email.
Great.
But I remember that we have a research group in PUC-Rio, and the French guy The French do that a little, using bot functions more in computations. I saw
Okay.
that
Send
twice.
it to us if you can. Copy me in that email, and
Yes, yes, of
and I'll
course,
see
of
you.
course.
If Sueli has an interest, I can bridge the gap and connect the two.
No, of course, we're here for
Cool.
that.
Yeah.
Try always to help.
Okay.
Cool.
Okay. That's so.
All right.